The title is "Can the use of exoskeleton reduce the biomechanical load for workers?" Just some organizational instructions. You are kindly invited to put on mute to avoid any noise during the presentations. The speakers are myself, Gabriele Caragnano. I am partner in PwC in consulting and technical director of the Fondazione Ergo. We have Simona Crea, researcher from the Scuola Superiore Sant'Anna from Pisa and advisor UVO. We have Marco Gazzoni, director of the Laboratory of Neuromuscular System Engineering, LISIN, from the Politecnico of Turin. And offline, we have Francesco the Great, Francesco Saverio Violante, professor from the Department of Medical and Surgical Sciences from the Alma Mater Studiorum, University of Bologna. Thank you very much for joining. The agenda today is the following. In a few seconds, I will hand over to Simona Crea for a short introduction to the exoskeleton mate, which is the first exoskeleton we have analyzed and studied. Second point will be a brief video by Professor Violante about the scientific approach to ergonomics. Then I will introduce the ESO-EAWS project with the participants and the main objectives. Following, we have the core content of this presentation. Professor Marco Gazzoni will present the lab protocol analysis and results out of this project, and eventually I will close the presentation showing the project results, the ESO-EAWS project results. So let's kick off. Let's go to the first point, and I hand over to Simona Crea, the first section of this webinar. Please, Simona, go ahead.
Thanks, Gabriele, for the introduction. Yeah, so I will briefly introduce you what UVO is, and I will introduce the mate exoskeleton. As Gabriele mentioned, is the exoskeleton that has been used during this project. So just a few words before starting about UVO. UVO is a spin-off company of Scuola Superiore Sant'Anna, which is a university in Italy. And in particular, the Biorobotics Institute is one of the research institutes of Scuola Superiore Sant'Anna, where basically starting from, sorry, maybe Gabriele, can you switch off the microphone?
There is someone with the open microphone. Please put on mute.
Yeah.
Sorry, Simona, go ahead.
No problem. From the initiative of a group of professors and researchers of the Biorobotics Institute, basically in 2015, basically raised the UVO company as a spin-off company of the university. And after that, in 2017, we basically received an investment from a joint venture between Comau and Ossur. So both are multinational companies. One is very active in the field of robotics automation, and the other one is a medical company which is very active in the field of prosthetics and bracing systems. So this partnership between, among these three partners, basically fostered the development of exoskeleton devices for different application scenarios. And in particular, the mate exoskeleton, which is the one you see in the picture here. This has been the first product that basically came out from this collaboration. So the mate device, which you can see here, is a device based on different technical features. We have a physical human-robot interface. We have a kinematic chain of passive degrees of freedom, and we have the active boxes, which basically provide the assistive action on the upper limbs. The device is a passive upper limb device, which aims to provide support to the upper limbs during repetitive or prolonged upper limb tasks. What you can see in this picture are the main design features, which basically lie on the kinematics compatibility, so the capability of the system to basically align its rotation axis to the biological rotation axis of the glenohumeral joint, which is the main joint involved in the flexion extension of the upper limb, and the limited and constant encumbrance around the human body. So the device has been designed to be compact around the body of the user and to maintain the encumbrance compact. That for safety reasons, it's important to avoid, impacting with the external environment. Of course, all the parts of the system are designed with rounded shapes, so that the device is also safe and safely interacts with the external environment, and has limited encumbrance at the neck and the head to avoid, contacting the head of the user itself during elevation movements. The device comes with two main sizes. So we have a small and a large size, but there are a number of regulations that allow to adjust the height of the trunk and the width of the shoulder, and to adjust also for different body anthropometries and shapes. So basically the device fits a wide range of human anthropometries. So we can go ahead and the very last point, of course, the device is on the market, has been on the market since months now. And of course, we received several feedbacks from users, from companies. We found several companies that basically are looking for solutions that can improve the health condition of workers, of course, in repetitive and strenuous tasks involving the upper limbs. And in particular, they're looking for solutions which are effective in reducing the effort of the workers and also may be usable and acceptable by the workers themselves. So that's a very important part. The reason why we promoted this study together with Fondazione Ergo and the Polytechnic of Turin was that we wanted to quantify the effect of the mate on the biomechanical load in an objective way, so that to provide a tool to the companies to basically assess the impact of using the exoskeleton on their ergonomics workstations and their workstations. So that's the reason why this project came out, and I will leave the floor to the other speakers so that they can give you more information and details about the project.
Thank you, Simona. Excellent. You set the scene. So I will introduce the next section of the presentation. We have a video from Professor Violante.
Di introdurre un aspetto di carattere storico che ci aiuta a contestualizzare poi quello che sapremo più avanti sui risultati del progetto. Allora, stiamo parlando del grande tema delle malattie muscoloscheletriche di origine lavorativa dovute a sovraccarico biomeccanico. È un tema noto da moltissimo tempo, di carattere storico, addirittura ne parlava anche il fondatore della medicina del lavoro Bernardino Ramazzini nel 1700 nel suo trattato sulle malattie dei lavoratori. L'argomento è oggi all'ordine del giorno perché con la riduzione fortunatamente delle esposizioni più pericolose, le malattie muscoloscheletriche in tutti i paesi più avanzati costituiscono la maggior parte dei disturbi che vengono riportati in relazione all'attività lavorativa. Quindi il primo problema di salute dei lavoratori in linea generale. Ora, perché è importante avere anche un inquadramento storico del progetto di cui parleremo oggi? Perché il punto fondamentale è che in particolare per quanto riguarda sia il tema della movimentazione manuale dei carichi, sia il tema del lavoro manuale, fino ad oggi, quindi fino alla comparsa recentissima della generazione di apparecchi di cui fanno parte gli esoscheletri come il MATE, il punto centrale per la prevenzione era stato quello dell'utilizzo dei dispositivi di assistenza meccanica. Vale a dire se abbiamo un'attività lavorativa che richiede un impegno muscolare alle persone considerato eccessivo, dobbiamo ricorrere ad artifici di tipo meccanico per poter ridurre questi requisiti. Perché questo? Perché l'enfasi fino al 2020 su questi aspetti? In realtà c'era stato un tentativo, in verità finito male, già alla fine degli anni '80, di pensare a dispositivi indossabili che potessero in qualche modo attenuare, se non risolvere, gli aspetti di patologia muscoloscheletrica collegati al sovraccarico biomeccanico. E mi riferisco in modo particolare al tema delle cinture addominali che erano state per un certo periodo di tempo propagandate come un dispositivo capace di ridurre il mal di schiena nei soggetti che facevano movimentazione manuale di carichi. L'idea ovviamente veniva dalla constatazione che questo dispositivo è un dispositivo che normalmente viene utilizzato dagli sportivi che fanno sollevamento pesi durante la loro attività. Quindi si pensava, beh, se fa bene o se è comunque gradito a chi fa sollevamento pesi, lo diamo a chi deve movimentare carichi per attività lavorativa, e questo potrà ridurre il carico di mal di schiena che queste persone sopportano. Ebbene, gli studi che furono fatti dall'Istituto Nazionale per la Sicurezza del Lavoro degli Stati Uniti in realtà non furono studi conclusivi, cioè alla fine si vide che l'utilizzo di questi dispositivi non risolveva il problema del mal di schiena di questi lavoratori, e quindi per anni il tema dell'utilizzo di dispositivi indossabili per ridurre il carico biomeccanico durante l'attività lavorativa di fatto è venuto, non è stato più al centro della ribalta perché appunto si riteneva che si dovesse comunque risolvere il problema del carico biomeccanico a livello di dispositivi meccanici di assistenza. Quindi si è sostanzialmente arrivati al concetto che il carico biomeccanico dovesse essere annullato. Gli esoscheletri fanno parte invece di una nuova categoria di dispositivi che si basano su un concetto diverso, cioè sul concetto che il carico, che vale la pena comunque di ridurre il carico biomeccanico, anche se non si può annullare completamente, perché questo è comunque costituisce un vantaggio per il lavoratore e può portare ad aspetti di carattere positivo. Ora, qual è il punto fondamentale del progetto di cui parliamo? È la dimostrazione dell'efficacia, e cioè non basarsi semplicemente sul razionale, cioè è possibile che questa cosa funzioni, ma dimostrare nei fatti, con metodologia scientifica rigorosa, che il dispositivo funziona. Il progetto di cui si parla oggi è una chiara dimostrazione ottenuta con metodi rigorosi dal punto di vista scientifico, che l'utilizzo dell'esoscheletro mate nel lavoro a braccia alzate riduce il carico di attività dei muscoli che vengono impegnati dalla persona durante questo tipo particolare di attività. Questa riduzione del carico muscolare è già un fatto positivo di per sé. Ovviamente l'augurio è che la riduzione del carico muscolare connessa all'uso del dispositivo possa poi portare alla riduzione delle eventuali patologie che possono essere poi collegate a questo tipo di attività. Però già oggi noi abbiamo la possibilità di avere la dimostrazione scientificamente rigorosa che utilizzare un dispositivo di assistenza indossabile, quindi un dispositivo che il lavoratore porta sempre con sé, che servirà sempre comunque quando dovrà alzare le braccia, senza dover essere legato ad un manipolatore di pesi o un eliminatore di peso che è nella particolare posizione in cui si trova. Ecco, quindi questi dispositivi funzionano, hanno un effetto positivo misurabile. Da questo punto di vista, al di là di tutto, quindi al di là dell'aspetto specifico, questa è la dimostrazione, una delle dimostrazioni che questa generazione di dispositivi ha un futuro davanti a sé. Vale la pena di investire su questi dispositivi sia dal punto di vista dello studio, quindi svilupparne nuovi e sempre migliori, sia dal punto di vista delle aziende, perché costituiscono un effettivo un dispositivo, diciamo, efficace nel ridurre il carico biomeccanico che i lavoratori devono sostenere in determinate particolari attività, come quelle ad esempio svolte a braccia alzate.
I hope that the subtitles were clear. I didn't switch on the audio because he was speaking Italian. Francesco can speak English, but this was a video we used during the same seminar we gave in Italian language. So after that, let's jump into our project, the ESO EAWS project. Francesco, Professor Violante had a clear vision. We wanted to demonstrate, to prove that the benefit from using an exoskeleton can be measured. And we listened from Simona Crea that one of the important needs from the market is the demonstration, is the measurement of the effect obtained from the use of the exoskeleton. So we from the Fondazione Ergo, we formed a team of experts involving, from one side, the laboratory of engineering of neuromuscular system and motor rehabilitation, so LISIN, from the Polytechnic of Turin. We involved Francesco Violante from the University of Bologna. Plus, we also involved the experts, let's say the application experts from the Fondazione Ergo. Fondazione Ergo is a neutral organization, non-profit organization representing the industrial sector, the industrial companies. We have several companies in our organization. We have also the unions involved in our foundation, plus some academic institutions, universities, and experts. In a few seconds, Professor Marco Gazzoni will present the method we adopted to measure the effect of the exoskeleton. So I will not spend any additional word on that. The starting point must be clear. the ESO EAWS project starts from one of the most important open challenges that can be summarized in the question: how does standard ergonomics scale change with the use of exoskeletons? So I leave the floor to Marco, and who will present and explain the protocol used in this project. Please, Marco, the word to you.
Okay, thank you, Gabriele. Yes, as Gabriele said, the specific aim of the experimental protocol we did in our laboratory was to study and evaluate the changes in muscular activity due to the use of the exoskeleton. The protocol was intended to provide information to update and change the EAWS scales to take into account the changes in muscular activity due to the use of the exoskeleton. So for this reason, the protocol was not focused on the simulation of a complete working task, but it was focused on specific postures that are considered in the EAWS forms. In particular, the tasks that we selected were from two forms of the ergonomic assessment worksheet: the postures and movement form and the upper limb that will be described in more details in the following. 12 subjects participated to the study, and the subjects were asked to perform four specific postures. The first one considered the shoulder abducted at 90 degrees and the elbow flexed and pronated at 90 degrees. The second one with the shoulder flexed at 90 degrees, the elbow flexed at 90 degrees and pronated at 90 degrees. And the 3 and 4 were the same than 1 and 2, but with the elbow extended. So we evaluated two conditions. The first one was a static condition where the subject had to maintain the postures in a static way. And then we considered also dynamic conditions where the subject had to move from the standard anatomical position to the posture and back with a specific cadence. More details about this: the static task was repeated for 5 consecutive times, and the subject had to maintain the static posture for 6 and 12 seconds, and 20 seconds. This was done to evaluate the effect of the duration of the static task on muscular activity. While the dynamic task was repeated for 15 times and lasted 3 seconds for each action. The tasks were performed in a random order, and during this task we acquired two information. We acquired for sure the information about muscular activity. We used standard bipolar surface EMG, detecting the signal from the main muscle group of the shoulder and of the limbs. So we acquired signals from the deltoid muscle, anterior, medial, and posterior heads, the vastus brachii, short head and long head, the tressus brachii, the lateral head, and the upper portion of the trapezius muscle. About the kinematic acquisition, we used the Vicon system with two main goals. The first one was to provide the subject a feedback about the correct posture. When the subject reached the correct posture on the basis of kinematic acquired with the cameras, we provided him a feedback that assured he reached the correct posture. And the second reason was the kinematic data were used to segment the EMG signals in order to extract information about the activity of muscles during different phases of static phase or dynamic contraction. In the next slide, we can see an example of signal acquired during a static condition, the posture 4. It is represented in the picture. We can see the information about the kinematics. It is represented the shoulder angle on the frontal plane. In blue, the kinematics using the exoskeleton. In black, the kinematics during a static task without the use of exoskeleton. And the same for EMG signal from the deltoid muscle, anterior, medial, and posterior heads. It is possible to see that from a kinematic point of view, there are no differences between the two conditions, with and without the exoskeleton. The variation in shoulder angle are below 1 degree during the wall contraction. And in the activity of about the activity of a muscle, we can see from a qualitative point of view that we can observe a decrease of EMG activity in all 3 heads of the muscle when the exoskeleton is used. We will see more quantitative data in the following. In the next slide, we have an example of a dynamic trial. As before, we compared the kinematics and the EMG, and also in this case, we can see that the kinematics is not affected in a significant way by the use of exoskeleton. We estimated the duration of the cycles during the dynamic task, and we obtained that the difference between the two conditions, with and without exoskeleton, is less than 0.1 seconds. Okay, so we have no effect of use of exoskeleton, the kinematics and timing of activity. About muscle activity, we can see that there are some differences during the concentric phase with a lower activity when the exoskeleton is used, while it is possible to observe, mainly for the posterior deltoid, an increase in the activity during the eccentric phase that is due to the fact that the subject had to activate the posterior deltoid to return to the anatomical reference position. Okay, so these are qualitative results. We assessed the data in using quantitative measures. And to do this, we combined the information obtained from kinematics and from EMG. We segmented the cycles, static and dynamic cycles, using the information provided by the kinematics. On the left, you can see the segmentation of the EMG signal using the information about shoulder abduction. And on the right, the segmentation in concentric and eccentric phases during a dynamic task. So when we segmented the different phases, we estimated a simple information about muscle activity, that is a amplitude information of the signal, the root mean square signal, the root mean square of the signal epoch. So we estimated the root mean square for each task and each action during dynamic conditions, and we average the RMS values that we obtain to have a global information of the effect of the exoskeleton on muscle activity. About the results, the group results that are shown in the next slide. Okay, in this case, we have the information about the posture effect on the activity of different muscles, biceps brachii, anterior deltoid, and so on, depending on the posture. The results, the statistical results, show that we have no differences between the trials that were the 6 seconds and 20 seconds trials. So we have no effect of the period of the length of the contraction on the muscular activity. And in this figure, we can see the box plot, the percentage variation in G amplitude between the use and not use of the exoskeleton, where positive values indicate a lower activity in the case of the use of the exoskeleton, so a positive effect of the use of exoskeleton. So in this case, for static conditions, we can see that in general, the EMG amplitude is always lower when we use an exoskeleton, with different effect on different muscles, but we always have a positive effect. The next slide. Oh, okay. So we had to decide how to use this information to provide a synthetic information that can be included in the scores of EAWS forms. So we consider different postures, and for different postures, we selected a subset of muscles that were selected on the basis of the involvement of each muscle in the different posture. So, for example, for posture 1 on the left, the main muscle groups are the trapezius and medial deltoid. And we only considered these muscles to obtain an information of the changes in muscular activity. What we did was to use the average changes in muscular activity between the use and not use of exoskeleton for all muscles considered for each posture. So in this case, we obtained a percentage reduction of 48% approximately. That is the average of the percentage reduction of trapezius and medial deltoid. While, for example, for posture 4, we considered trapezius, medial deltoid, anterior deltoid, and posterior deltoid because all heads of the deltoid muscle are involved in this static posture. Okay, so the percentage reduction was the output of this protocol for the static condition that was then used to adapt the scores of EAWS values. About the dynamic trials, the results are similar, but we have to consider that, for example, in the case of posterior deltoid, you can see that mainly for posture 2 and posture 3, in the case of eccentric phase of the movement, we have an increased activity of this muscle during the eccentric phase. This is reasonable because since the exoskeleton support the arm in with the elbow, with the shoulder flexed at 90 degrees, it is necessary to activate the muscle to come back to the anatomical reference position. However, when we put all the results together, as before for the static trial, in the next slide, we can see the percentage reduction of muscular activity for the 4 postures. But for example, in this case, for posture 2 and 3, we have the trapezius, anterior deltoid, posterior deltoid, and biceps brachii. For trapezius, anterior deltoid, and biceps brachii, we have a positive effect of the use of the exoskeleton, while for the posterior deltoid, as we saw before, we have a negative effect. But in any case, the percentage reduction is always significant, and it is approximately 25%. Okay, so this protocol was focused on the postures that are considered in the EAWS forms, and we provided as output a global information that was synthetic information of what we observed, that was synthesized in a percentage reduction, considering all the muscle groups that were involved in each posture. And this was the output that we provided to Fondazione Ergo, that worked on but in the following steps to adapt the EAWS scores.
Thank you, Marco, for the excellent synthetic presentation. Of course, we are available to share the full project report with more details. But let's see what happened after this step. The synthetic results were provided to the group of experts of the Fondazione Ergo. Fondazione Ergo is the owner and developer of EAWS. EAWS is a product, a system, an ergonomic analysis system developed in the period 2005-2008. It was a co-development made with the Technical Institute of the University of Darmstadt, and it was a fantastic collaboration. So the result was this comprehensive system. You have a snapshot on the left side of this page. EAWS is made of 4 pages, A4 pages. Considering the main areas of generation of biomechanical load. So we have the body postures in section 1. We have action forces, body forces in section 2. The manual material handling in section 3, and the upper limbs, the repetitive motions in section 4. EAWS is currently used by many companies to improve and redesign or design from scratch a product and a process, mainly a process, I would say, in order to avoid ergonomic bottlenecks causing risks. EAWS, as I said, is a comprehensive system, and if we compare EAWS with the traditional SEN ISO ergonomic risk assessment, we have a similar approach. So we consider in a load situation. In the case of EAWS, we are considering all load situation, from manual material handling, body postures, action forces, and repetitive motions. We consider, of course, the relevant characteristics of the intended user population. So we have, different data for different percentiles of the population, and differently from the traditional ISO standards, we sum the risk scores for all stressors modes, and by stressor mode I mean the different load situation per time unit. So the result is a risk evaluation according to the traffic light scheme, considering the overall load generated by a work task, repetitive work task. EAWS today is widely spread around the world. It is used in different sectors, industrial sectors, from automotive, large domestic appliances or small domestic appliances, in aerospace and defense, agricultural and capital equipment machines, rail, supply, machinery, textile. And we have set up a platform, an EAWS platform, to sustain the scientific future developments of EAWS and to provide the users with the necessary documentation, training and information in order to facilitate the use of EAWS. We have today's 3 user groups. One is in Italy. You see some of the key users listed in this page. We have a German user group, and we have also an Hungarian user group. We are going to, set up other user groups in other countries. We have in red 2 companies, FCA and Volkswagen, which are, let's say, key user groups. So they are active member of the platform, and they are very helpful and supportive in addressing the strategic and technical future development of EAWS. Just a few numbers. These are numbers coming from the MTM network. EAWS is one of the official system of the technical MTM platform. So it is distributed in all countries with the same rules and with the same material. EAWS material has been translated in almost all the languages, including Chinese and of course the main European languages. And today we estimate that there are more than 600,000 workers working in workplaces which have been evaluated with EAWS. So as I said, EAWS is structured in 4 sections. Highlighted in green color here, you see the sections which are impacted by this type of exoskeleton, and specifically the mate exoskeleton. So we have an impact on section 1, so on the body postures. Of course, the postures involving the shoulder, so not all the postures. In section 1, we identify 16 lines for 16 different postures, out of which we have some lines regarding the shoulder postures, which will be exactly the lines affected by this project. In general, we can using as input the figures received from the laboratory phase. We have grouped the percentages obtained and with a conservative approach, even if the average of the percentages were above 30%, we limited to 30% the effect on the shoulder, following some criteria which I'm going to explain in a few seconds. The other section impacted is section 4. Section 4 is very important because it regards the repetitive motion of the upper limbs. And as you know, when you go in industrial sectors with repetitive cycles, the upper limbs usually are the part of the body more actively involved in work activity. In this case, we have a reduction of 25%, which is less than the impact on the static body posture in section 1, because in section 4 we have dynamic situations, and in that case the reduction is limited with respect to the static posture, because we have after the concentric motions, we have the eccentric motions, so the return motions, which are constrained slightly by the exoskeleton. The EAWS scoring scale follows the ISO-1000 standards, according to which the output is often represented by a traffic light signal. So from EAWS has a scale ranging from 0 to 25, indicating a green area, so an area with low risk. From 25 up to 50 point, we have a medium area, yellow area, and in above 50 point, we enter into a high risk area. This is just to understand the output of the scores. But let's look at the scale, starting from section 1. So this page refers to section 1. Section 1, as I said, has 16 different lines. Each line represents one specific body posture. Those are what we call the symmetric body posture. Then we have also a table to manage the asymmetric postures. We have 3 types of asymmetric postures. We have the trunk rotation, the trunk bending, and the far reach of the arm. In this case, in this project, we considered only the far reach as a asymmetric posture. So how did we modify the score? Well, we basically used as a reference line 10 and 11, which is the sitting posture. Line 10 is sitting with the elbow reaching the 90 degrees angle, so basically with the elbow at the same height of the shoulder, which is very typical and common in industrial work. And we added to the traditional line 10A, which is sitting with elbow at or above shoulder level, without any support. Line 10B is the score reduced thanks to the use of the exoskeleton. And the difference between the line 10A and 10B is exactly 30%. Why did we use line 10A? Because the load in that posture comes definitely from the shoulder. The rest of the body is sitting in a good position, so all the load is generated by the shoulder. In the other postures like 5 and 6, we have a small amount of load coming from the standing position. Even worse, in line 14, a larger part of the score is generated by the body posture, which is uncomfortable, like crouching or kneeling. So in using line 10 and 11 respectively for the elbow at shoulder level and the hands above the head level, which is more extreme, we calculated the reduction of score, reducing by 30%, and we used the absolute amount of score reduced to reduce the score of line 5A and 6A and 14A, calculating in this way the score, the corresponding score with using the exoskeleton. So if you take for example line 10A for the 4 points, without exoskeleton and 2.8 with exoskeleton, the reduction is 1.2 points, and the same amount is deducted from line 5A, for example, 5 minus the 1.2, the result is 3.8. So this is the principle we used. You see different scores, growing from left to right, and this is due to the fact that each column has a different duration. So if you go from left to right, you have the same posture but with a longer duration. And of course, with a longer duration, you have a higher, a more intense load, and therefore we have a higher score. The same logic has been applied to the table on the bottom of the page, the gray table, where you see the reduction of intensity score for the far reach, for the asymmetric posture. So 1, for example, is the score if the intensity of the extension of the arm is 60%, and 0.8 will be the intensity of the score in case of using the exoskeleton. So this reduction is less than the full reduction of 30%, because we know that from the leasing study that in a far reach position the reduction is less than 30%. If I remember well, it is around 28%. So for this reason, we set to 25% the reduction in case of asymmetric posture. Going to section 4. Section 4 again is for the upper limbs, repetitive motions. In this case, the average reduction was in between 25 and 30%, and we set the average reduction to 25%. And as far as the shoulder posture points, we reduced the score of the shoulder posture point by 25%. This is a relevant reduction. It's important because following the EAWS logic, the final load, the final score is the result of the product between intensity and duration. The posture points are part of the intensity points, which multiply the duration. The typical duration in an industrial sector is around 7 points, which means that if you reduce 2 points of posture points, you reduce 2 points of intensity, which multiplies 7 points of duration. So 2 times 7 means 14 points, which is a large amount. If you remember the scale, from 25 to 50, we are in a yellow area. So reducing the 10, 12, 14 points, it's a big benefit. So that is the the summary of the result. So we started from the objective to to respond to the question, how does a standard ergonomics scale change? So we designed, we have measured the effect of reduction of muscle on the muscle load, and we translated this reduction in a reduction of points of score in the EAWS lines, in which the shoulder plays a fundamental role. As a result of this study, we defined a category of exoskeleton, summarizing some technical characteristics of the exoskeleton in order to open the way to future products willing to achieve the same kind of certification. So we define the S01 category. S stands for shoulder, 01 because this is the first category. Mate belongs to this category. So the technical specifications which you see on this page are satisfied by the mate technical specifications, which means that if in the future a new product, a new exoskeleton will go through a similar laboratory test and respects these characteristics, we certify that exoskeleton, and as a consequence, the EAWS form can be combined and used in combination with that exoskeleton. To give you a practical, concrete idea of the effect, I'm gonna show a very short example in which this operator, makes a very easy task. Is hanging on a moving skyline, some hooks which are used to hang metal panels. This is a typical operation done in a painting department. So the operator in this case is hanging with using the right arm, going back and forth to get the hooks and hooking them on the skyline, moving skyline. So it's a very simple operation. So by looking at this operation, I want to underline and give you an important message. The use of exoskeleton is not the unique and final solution. The exoskeleton is a good tool, among others, to improve the ergonomic condition. In my experience, in my opinion, the best solution is always a good method design. So starting from a good ergonomic method design, usually all the bottlenecks and the main constraints, the main risks are avoided. If there are no other opportunities, if we have made everything possible, the use of exoskeleton is one of the good solutions. In this case, the use of the exoskeleton in this very simple job, honestly, very simple job, would reduce the score from 37 points approximately to 30 points. So it's a reduction, a significant reduction. And what does it mean? Well, if the EAW score reduction, which impact on the ergonomic work allowance, in this case, the company, in this example, the company is using the Ergo MTM model. In the Ergo MTM model, we combine the ergonomic allowance with the overall load index calculated through the EAWS. So on the graph on the right side of the page, you see a model, a curve. On the horizontal axis, we have the EAWS index, and on the vertical axis, we have the ergonomic allowance. What is an allowance? For those who don't know, an allowance is a percentage applied on the basic time, usually calculated through MTM. So MTM calculates a basic time, so a time without any allowance, and the ergonomic allowance is calculated, applied on a basic time in order to obtain a standard time. A standard time contains the basic time plus an extra time allowed to cope with, in this case, with ergonomic conditions. So by using this model, widely used in many companies, in several industrial companies, by improving the ergonomics, we are reducing the cost, which is quite interesting. The effect of ergo allowance reduction is improved productivity, because we are reducing the standard time, reducing the cost, and in this way we are saving. We have money saving to pay back the investment for ergonomic improvement. So by reducing of 7 points in this case, we are reducing also the allowance, generating also a reduction of cost, which is an extraordinary incentive for the companies to improve ergonomics. Beyond, besides the ethical reasons, which should be enough, to justify ergonomic improvements. But we know, we are human being living on the earth, and the money often is a relevant factor to push for actions. So this is the summary. In summary, what we have done in this last page. You have the coverage, the extension of the 1MTM network. We from Italy, we support companies in Italy, including France, Spain, and Turkey. But we cover more or less almost the full globe. So through the MTM, the 1MTM network, you can get the knowledge, the trainings, and the material you need. So if you have any question, please don't hesitate to contact us. That's it.